Both open circuit and short circuit terminations result in gamma having a magnitude of 1, which corresponds to total reflection of the voltage wave. The outermost edge of the Smith chart corresponds to total reflection, where the magnitude of gamma is 1. The closer a load is to the edge of the Smith chart, the more reflection it experiences. These are circles of constant magnitude of gamma. Smaller circles indicate values closer to a match, while larger circles indicate values closer to total reflection. The exact numerical value of gamma may also be read off the chart. First, the magnitude of gamma may be found by measuring, with a compass, the distance from the center of the chart to the plotted impedance. The corresponding magnitude of gamma may be read off the scale at the bottom of the page. So if a load impedance is plotted as 0.6 plus J0.4, we can measure off this distance on the Smith chart, and then measure off that same distance on the scale at the bottom of the page labeled reflection coefficient. So here we see that the magnitude of gamma for this load is approximately 0.34. Then we can find the phase of gamma by drawing a line from the center of the Smith chart all the way through the radial scales at the outside of the chart and reading the phase off the scale labeled angle of reflection coefficient in degrees. So for this example, the angle of gamma is 121 degrees. So the reflection coefficient we've just read off the Smith chart is 0.34 at an angle of 121 degrees. Let's double check these values mathematically. We said that a normalized load impedance of 0.6 plus J0.4 is 30 plus J20 ohms. The reflection coefficient then is given here, and indeed this does work out to 0.343 at an angle of 121 degrees. So we get the same number graphically as we do mathematically. Note that there are similar scales at the bottom of the chart for reading off standing wave ratio, return loss, transmission coefficient, and other design values. Now look at this scale around the outer perimeter of the chart, labeled wavelengths toward generator. This scale is used for calculating Zin at a distance from the load, as we did in the transmission line module. Note that the range of this scale goes from 0 to half a wavelength. That's because the input impedance repeats every half wavelength. Adding 0.6 wavelengths of transmission line will have the same effect as adding 0.1 wavelengths of transmission line.